Okay, so let's take a look at this thing called bond order. And ever since we started studying bonding in honors chemistry, we referred to them, we've got different types of bonds that look like this or maybe like this, and we always called one of these, we called this a single bond, we called this one a double bond, and we called this one a triple bond. In higher level chemistry, they refer to this as bond order. So a single bond has a bond order of 1, a double bond has a bond order of 2, a triple bond has a bond order of 3. But what does this mean? I mean, we know that triple bonds are way stronger than double bonds. Everything that has nitrogen in it, like TNT, trinitrotoluene, is so powerful because nitrogens always have these really strong, triple bonds. Breaking oxygen, not quite so difficult, but harder than breaking bonds for things that are single bonds. Well, what's going on here? And that pertains to something called molecular orbitals. And I'll do my best not to melt your brains on this. So here we go. So here's a question that we've probably not really ever asked. What happens when hydrogen atoms bond to form a molecule of H2? And we know that hydrogen's a pretty simple molecule. It only has one electron, and so it really is only using the 1s orbital. And so two hydrogen atoms forming a bond are going to, in a sense, use this s orbital, kind of like that hybridized model, except there's no other orbitals to hybridize with. So the electron that each hydrogen atom has are going to occupy both of these orbitals when the bond's finished. So what does that mean? So here is a slightly better picture of it, and here's what happens. When these two individual atoms bond, they're going to make I guess we call it a hybridized orbital out of both of their individual ones. And what happens is this. I mean, these orbitals, they're just spaces where we predict we could find an electron. And what appears to happen is that whenever these two orbitals mix to form one hybrid orbital between both atoms, one of two things happen. And that is that half the time the two orbitals combine to form a nice space in between the nuclei where the electrons exist. We're going to call that a bonding orbital. And since this exists in line with the molecule, it's a sigma bond. So we're going to call that a sigma 1s. And since it is an orbital that makes bonding easier, we'll call this the bonding orbital. Half the time, though, these two orbitals repel, they fight each other, they just make a bunch of static, and they don't create anywhere for the electrons to exist. We're going to call this the anti-bonding version, and it happens just as often. But because it doesn't promote bonding, and because we know that atoms form bonds because it lowers energy, it doesn't promote bonding. We're going to call it the anti-bonding orbital. And because it makes things harder, it's higher in energy. So notice that this diagram, the bonding version is slightly higher. To indicate that this is the anti-bonding version, we're going to call it the sigma 1s star, or sigma star 1s. It's the anti-bonding version between two 1s orbitals. Now, how does this work to promote bond order? How does this work to make a stable situation between two hydrogen atoms? All right, this is called a molecular orbital. diagram. This arrow is energy. And the higher up in energy, the less, the harder it is for this to form. We want definitely to form bonds with lower energy, just because remember Hund's rule says we want to fill the orbitals with the lower energy first. And so here's what this diagram is telling us. Each of these 1s orbitals comes from a hydrogen atom. We know that hydrogen has one s electron. And so these are what we call atomic orbitals, what you might see abbreviated as AO. When atomic orbitals combine, as we've said, they do two different things in equal amounts. They form molecular orbitals, what we're going to call MO, and sometimes they form this nice bonding version, which is lower in energy and promotes the bonding of these two atoms. Sometimes they form the anti-bonding version. So when we are putting these two hydrogen atoms together, we're going to fill both of these orbitals, but we're going to do it like we did with regular electron configuration, and we'll fill the lower ones first. So notice that this hydrogen atom has an electron, a single electron because it's 1s, and this hydrogen atom has an electron. When we combine them, we're going to put them in the lowest available energy orbital. That's the 1s formed into the sigma 1s, the bonding orbital. Notice that there is nothing in this orbital, the anti-bonding. So we're going to calculate something called bond order. We'll abbreviate that, feel free to laugh, BO. And it's going to be the number of bonding electrons minus the number of anti-bonding electrons. And we're going to divide both of that by 2, excuse me. So, looking at this model, how many electrons are in a bonding orbital? 2. How many electrons are in an anti-bonding orbital? 0. What's the bond order for hydrogen gas? It's going to be equal to the number of bonding orbitals, which is 2, minus the number of electrons in anti-bonding orbitals, which is 0, divided by 2, and that is 1, which we knew because hydrogen atoms form single bonds, so their bond order is 1. Let's try this with a molecule that we know doesn't form. So let's take this orbital model and try another one. I'll show you what I'm talking about. Okay, let's take an atom that we know never forms bonds. Let's take helium. We know helium's got an electron configuration of 1s2. That means each one has got 2 electrons. And we know this is a noble gas, so it never bonds with anything else. We've never seen that. So why? Why not? Why doesn't it ever form bonds? Well, let's do this. We know that each helium has got 2 electrons, right? 1s2, these are the atomic orbitals. And each helium has got 2 electrons. That means there's a total of 4 electrons that we have to stash. And 1s orbitals can only hold 2. So where are they going to go? Well, we've got 4 electrons we're going to stash, and just like Hund's rule says, we'll put the first 2 in the bonding version, the sigma 1s. We'll put the remaining 2 in the only available place there are, which is the sigma star 1s, the anti-bonding version. And so what's the bond order? we are going to say that the bond order is equal to the number of bonding electrons, which in this case is 2, minus the number of anti-bonding electrons, which in this case is 2. We're going to divide that by 2. So the bond order is what? 0. So that's all we do for this one. Now, it gets a bit more complicated because we're going to get into some larger orbitals, but that's the basics. And if someone asked you what the electron configuration for a molecule of molecular hydrogen was, because you know it is sigma 1s2, because that's where the electrons are. The electron configuration for helium would be, sigma 1s2, sigma star 1s2. And because the bond order is 0, bonds between those atoms never form. All right, it's time to go big. Now, if we just stayed at energy level 1, things would be much easier, but unfortunately, we're not. We're going up to energy level n equals 2. And so here's how this one works. We know that s orbitals do this bonding and anti-bonding thing. And so it stands to reason that the 2s orbitals act the same way, where they can form a sigma 2s bonding and a sigma star 2s anti-bonding orbitals. But what about the p orbitals? And that's where things get a little weird, because p orbitals can form bonding and anti-bonding orbitals too, and those are the orbitals that are involved in making pi bonds. So let's take a look at what's going on with p orbitals, and I'm just going to throw this out there, and that is that when p orbitals combine, sometimes, and remember these are making the pi bonds, the p bonds are making the pi bonds, that when they combine to produce a bond that favors bonding, we're going to call that a pi bonding orbital, we'll call that pi 2p, and that when they form an anti-bonding orbital, we'll call that pi star 2p. So what does it look like in terms of energy? So this is the energy level diagram for orbitals at energy level 2. It looks weird, just go with it. Let's try this with oxygen, molecular oxygen, and we've said that oxygen forms double bonds, and so it should be a bond order of 2. And let's remember that each oxygen has 6 electrons in the valence, and since there are 2 of them, that means a total of 12. So we're going to put the valence electrons from one oxygen on this side and on the other on this side. So they each have 6 valence electrons, because the electron configuration, let's remember, is 2s2, 2p4. So each of these oxygen atoms has 2s2, 2p4, and when we combine them, we'll use Hund's rule. So we're going to put 2 of them in the sigma 2s, and now that's full. 2 more go in the sigma star 2s, and now our 2s orbitals are filled. We've got 4 electrons in the p's. So we'll Hund and Aufbau. Hund's rule means, I've been saying Hund all this time, Aufbau are lower in energy. Hund's rule says they should stay separate, so there's 1, 2, 3, 4, 5, 6, 7, 8. So how many electrons are in bonding orbitals? 1, 2, 3, 4, 5, 6, 7, 8. So calculating our bond order is bonding electrons minus electrons in anti-bonding orbitals. 1, 2, 3, 4. What's the bond order for oxygen? 2, which is exactly what we thought. Okay, take this for a spin, and I'm sure it's going to look a little weird the first time, but I'll provide these diagrams for you and just fill them in order. Keep your electrons separate a la Hund, and keep them in the lowest energy level, a la Aufbau, and you should be fine.